Hi, welcome back, and welcome to Handout 11, which has to do with evaluating projects using our discounted cash flow models or DCF models. So let's jump right in. So we've already learned, as we've talked about several times, a project evaluation method called the balance sheet review method. And we all know how that works. You start with our GAAP assets, we morph them into market values or replacement values, and we add any market brand value or something like that that has not been included previously, subtract our liabilities, et cetera, et cetera. And the problems that we've seen with that are that, first of all, we need a balance sheet. Not all projects have balance sheets. And secondly, it's very difficult, in most cases, not all cases, to estimate the true market value of the assets on the balance sheet and assets that aren't even on the balance sheet, like brand value. And finally, with this, we're always assuming the future looks like the past, and there's no enfranchised growth and things like that. So, as I've alluded to previously, that motivates us to try and find other methods we can use to evaluate financial projects. The nice thing is that we can evaluate any project if we look at its time normalized cash flows. These are what I mean by time normalized is the present value equivalent of each project's cash flow. So we have to remember the time value of money, and we have to remember, well, this cash flow happens here in a year, but what's its equivalent at t equals 0? And we use our PV-FV formulas to make that translation. So using these time normalized cash flows and an understanding of how risky a given project is, we're going to be able to evaluate any project that we want. And when we use this approach, these methods are called discounted cash flow methods. And I think on that note, I'm going to pop out visually and I'll put in Excel and I'll keep going. Okay, so let's keep going here. Give me just a second. Okay, and let's see what we have coming up here. There are three important discounted cash flow methods. The first is net present value, and the second is our benefit cost ratio, and the third one is our internal rate of return method. We're going to have to understand all three of these to see how they work and to see what their limitations are and that kind of thing. But some key points for all of these methods, we always want to be sure to evaluate a project for one participant at a time. So definitely don't mix something like a sponsor, a bank lender, a building owner. We want to pick one of those players and evaluate the project from their perspective completely. And we're only going to consider for this project cash flows in and out for the participant that we've chosen to analyze for. Okay, so if there is the mother of all mountains of cash sitting in this project, it's not going to affect us. We're only going to consider cash flows in and out of this project to and from the participant we've chosen to analyze. And now, for the first time in time value of money, we're always going to be using a proper sign convention for all of our cash flows in all our equations and on all our cash flow diagram. So we're not going to be anymore saying, oh, okay, well, the algebraic signs might be wrong, but we're going to use common sense to suss out what's going on. Now we're always going to use a proper algebraic sign convention. Okay, and that's true for all three of these DCF methods. And also, we're going to choose to evaluate all the projects that we look at t equals 0. Okay, and what that means is we want to discount all of those future cash flows back to time t0. Okay, so these are our key points for all three of these methods. And we have some key assumptions that we need to apply to use these models, these discounted cash flow valuation models or methods. So for now, let's consider all of our projects are independent, and also let's assume we have an unlimited budget. In addition to that, we're going to have to assume all of the marketplace and investor implications that I've covered previously. So I covered some of those in chapter 8 and some more in chapters 9 and 10. There was one page that just had this horrific list of all the assumptions needed for our models. That horrific list still applies. Plus, we have independent projects. Plus, we're assuming an unlimited budget. So alternate to the independent projects' unlimited budget assumptions, we could consider mutually exclusive projects or projects with limited budget, which is the same as capital rationing. And we will do both of these things in the next chapter. All right, so let's march through our methods one at a time here. And let's start with the NPV method and see what it is and how it works. Okay, so the NPV method for evaluating a project first says, as is the case with all these methods, consider just one participant. And then for that participant, we want to estimate all of her cash flows for the project. And again, now we're going to be using a proper algebraic sign convention. And next step, once we've estimated her future cash flows for this project, we want to normalize these cash flows to t equals 0. How do we do that? We take the present value of each one individually, just like we've been doing, and we want to be careful now to include all cash flows, including any at t equals 0. So this is a little bit different than what we were doing in chapter 8. In chapter 8, we were considering only the future cash flows and getting the PV of those. So in this chapter, we're also going to include any cash flow that happens at t equal 0. Okay, and once we do that, once we've estimated this participant's cash flows for this project and we've normalized them all back to t equal 0, now they're comparable on an apples to apples basis. That's why we had to discount them all back to t equals 0, because now they're on an apples to apples basis and we can compare them. How are we going to compare them? We're going to simply add them all up. So discount first, then add. That's always our rule, right? Discount first, then add. Okay, and now, since everything is normalized, if the sum of her beautiful normalized cash flows for this project is greater than 0, the meaning of that is that she estimates she's going to get more normalized cash out of the project than she puts in. So that's going to be a very helpful thing, i.e., if that's the case, If she gets more normalized, time normalized cash out of the project than she puts in, then she should go ahead with the project. And if the sum of her normalized discounted cash flows is less than 0, she should pass on this project and not worry about it. Okay, so mathematically, how are we going to set up this NPV method? Well, we have to start with a definition of the net present value. So the net present value of a project is defined to be the present value of each cash flow for this project, for this participant, including anything she pays or receives at any time, including now time t equal 0. Again, a little bit different than what we were doing in chapter 8. So with that definition, we can now write mathematically what we call the NPV formula or the NPV equation, depending on who you're talking to, okay? And it looks like this. It says the NPV of a project is equal to the sum of the individually discounted cash flows. So you see the way this sum is working. For cash flow I, first discount it, do that to every stinking cash flow, then after you've discounted them all, add them up, okay? So now we have the subscript here for I, the index rather, for I, has changed a little bit. It used to be from 1 to the number of future cash flows. Now it starts at 0 to the total number of cash flows for this participant in this project. And as has always been the case, TI is the time of cash flow I. Okay, so I think that's looking good. Let's make sure we've got everything here. Like I said, the index starts at 0, not 1. And the other thing that we might want to say here to reinforce is that we are going to be using a proper algebraic sign convention where cash inflows are going to get a positive sign and a cash outflow is going to get a negative sign. So for a simple case, I'll present quickly another way to think about this. So let's say we were paying today for a stream of future cash flows as illustrated here. Okay, so we have something like this where CF0 could be the price that we're paying for a bond, and these are the contractual cash flows that were promised from the bond contract. So we could get the NPV for the bond buyer for this contract, applying our NPV formula here. And if we do that in this case with these three cash flows, it's going to look like this for this example. Okay, so here's our minus CF0, right? Always a proper algebraic sign convention now. That's negative. That's the cash outflow that we pay to get the contract, which hopefully is going to get us these future cash flows. Okay, and then we take future cash flow 1, discount it back to its equivalent at t equals 0. Same thing with cash flow 2, same thing with cash flow 3. Bring them all back to their equivalent at t equals 0. Now everything is on an apples to apples basis. And I can just rewrite this a little bit here by putting brackets around all the future cash flows that our participant is going to get here, group those all together, and subtract from that the cash flow she has to pay at t equals 0. So if we organize things in that way, the NPV can be thought of here as the present value of the future cash flows that are promised by the contract minus today's purchase price. So that helps give us a nice qualitative understanding of what's going on here. And with that understanding, we can say we'd want to invest in this project if the present value of the future cash flows is greater than today's purchase price. And if that's not true, then probably we don't want to invest. Okay, so we've got our NPV method, and we have this great equation that we're going to use to compute the NPV of a project. But we need to think a little bit about what cash flows exactly should we be putting in here, and what discount rate should we be putting in here in light of our discussion about risk in the last two chapters. So for cash flows, we always want to use, just like we did in the past two chapters, we want to use our project risk specific expected value cash flows. So for example, this is very similar to something that we did in the last chapter. We could say cash flow 1 is what's contractually promised. It's $10. It's what we're going to get if the project goes perfectly. We assign, after a lot of work, after maybe 2 days worth of work, we say, we think there's a 95% probability of that happening. Okay, and on the other hand, we think there's a 5% probability of getting 50% of that. If there is a problem with stupid managers, if there's mismanagement, we believe we'll only get $5, but we do assign that a very low probability. So what would we want to use as our project risk specific expected value cash flow for cash flow 1? We would want to say 95% times 10 plus 5% times 5. And if you work that out, check to make sure that you agree with me, but you get 975. So we'd say on average, over the long haul, we keep repeating projects like this 100 times, 1,000 times, 10,000 times. 95% of the time we get 10, 5% of the time here we get 5. So on average over the long haul, we get 9.75. So what are we going to do with our discount rates? What do we want to plug in for R here? Well, happily, we thought about that a lot in the last chapter. And what we always want to use for our discount rates are our opportunity costs of capital, which, as we know, can be described as either ROCC for our opportunity cost of capital, or RM for our market or our industry. Either one is fine. They mean the same thing as far as we're concerned in this chapter. So now that we know the quantities to use here, our project risk specific expected value cash flows, and our opportunity cost of capital for our discount rate, we can rewrite the NPV equation like this, where now the cash flows here are our project risk adjusted cash flows, and instead of putting a generic discount rate R in there, let's go ahead and put in ROCC for opportunity cost of capital. Otherwise, the NPV equation is unchanged here. So this is the way we're going to be using it for the rest of the chapter and the rest of the term, and for those of you going on in finance, for the rest of your life in finance. So there are two important properties of the NPV formula. So the first one is that NPVs of our opportunity cost investments, as we learned them in the last chapter, are always equal to 0. So let's see how this works. So let's say our investing mission in life is that we invest in very low risk short-term opportunities, say about 1 year. Okay. And then we know the opportunity cost of capital using our opportunity cost of capital model is going to be the known interest rate for a diversified set of alternative projects with similar risks. So what would we find in this case? There are several things we could do, and one would be we could go out to a place like bankrate.com where there are a lot of CDs on offer, and we could just pick 100 and short-term 1-year CDs and find that take the average promised compound interest rate for those CDs, find that to be 5%, and we could look up the average price of the CDs, which is usually right around 100. So we'd find something like 100, and that would be fine. Another thing that we could do is we could be a little lazier and go to the Mint Exchange Traded Fund, which, as we learned in the last chapter, holds many short-term CDs and treasury bonds. And we could literally look up on the site for the Mint ETF, look up at PIMCO's website, the purveyor of this exchange traded fund, what their future yield rate is, discount rate, yield to maturity is for this. And they publish this frequently, and let's say we found 5%. So either of those would be fine. We could construct this diversified portfolio ourselves, looking at CDs at bankrate.com, or we could simply pick an ETF that's already done a lot of that for us. Okay. So in this case, our opportunity cost investment is going to be buy a portfolio of the CDs or buy shares of the Mint ETF. In either case, we've found from our research that those have a discount rate, yield rate of 5%, okay, as found by looking these up. Okay, and so the NPV of these investments is going to be found by just plugging into our NPV equation here. Okay, so if we bought, we'd pay 100 here. Okay, and then we would get what after a year, these are for 1 year investments, we would get 105 divided by 1.05 because our opportunity cost of capital is 5%, okay, raised to the 1, okay, and that is equal to, I think, what, minus 100 plus 100 when you work all this out, and that's equal to 0.0. Okay, and let me just put in a little bit of the algebra for this guy. So this is going to be CF0 plus CF1 divided by 1 plus RCC raised to the 1. Okay, so that's where I got that from. Okay, so how can we think about this qualitatively? Okay, in this case, what we've seen up here with the algebra done for us and plugging in the numbers is that the present value of the cost of the cash flows, that would be our minus 100, that would be to buy the portfolio of CDs right now at 100, okay, that's equal to the present value of our income cash flows, the cash flows where we get money back. So here's our income cash flow, and here's our discounting of that. And what we find is this one is equal to, in magnitude, this one. So we add them up algebraically and we get 0. Okay, second important property of the NPV method is that if we find mission-fitting investments with NPV greater than 0, we should make them. Let me just put a star there. Whoops. I'll try to put a star there. See what happens. There we go. Okay. And that follows directly from property A, okay? If we put our money into an opportunity cost investment, we're going to do as well as our opportunity cost investment. But if we find something with an NPV that's bigger than that, it's implying we expect to do better. So we should go ahead and invest whenever we find the NPV of a project is greater than 0, okay? And that gives us a great rule for applying the NPV formula, which is simply going to be invest in a potential project if the NPV is greater than 0. If it's less than or equal to 0, don't bother, okay? Just what could we do? We could put the money we have into our opportunity cost investment, and that would be great. Okay, so what are our steps for using the NPV evaluation method? So here's a little recipe showing step by step how we apply this. So the first thing we're going to have to do to use the NPV method is to know what our investment mission is. We have to define it. We have to be rigorous about our investment mission. So for our short-term, low-risk investor that we talked about a lot in the last chapter, this would become, our mission statement would be, we invest in guaranteed return, one-year opportunities where the opportunities are strong, okay? So similar to something like US government guarantees, strong guarantees. Okay, so that's number one step to apply the NPV method. Okay, and second step is we've got to go out, just like we did in the last chapter, and find an opportunity cost investment and get our opportunity cost of capital from this, exactly like we did in the last chapter. So once again, for our short-term, low-risk investor, her opportunity cost investment is going to be a set of many one-year CDs that she found out at bankrate.com or shares of the Mint ETF, and her opportunity cost of capital is going to be the average of the interest rates shown on the CDs. And let me just do this, shown on the CDs at bankrate.com, or the published interest rate of the Mint as published by PIMCO, and we saw how that worked in the last chapter. So we know our mission, we've found our associated opportunity cost investment and our associated opportunity cost of capital. That's step 1 and step 2. And step 3 is now we go looking. We go looking around the world for projects with similar riskiness. These are projects that fit our mission statement. Right? Or another way to say this, projects in our investment milieu, something like that. I can't spell in English, let alone French, but in our investment galaxy, in our investment milieu, you get the idea. We have to have similar riskiness. Otherwise, they don't fit our mission. They're not in our milieu. Okay, so once we've got this potential project, then we're ready to determine its cash flows, and we want those to be project risk adjusted. And once we've got our project risk adjusted cash flows, we already have our opportunity cost of capital, and we can go ahead and solve for the NPV of this project using our NPV formula here, with again our opportunity cost of capital here, and here our project risk adjusted cash flows. And then we apply this simple NPV rule. If the NPV is greater than 0, we want to go ahead and invest. And if the NPV is less than or equal to 0, don't go ahead. And I put equal 0 down here. Why? Because it's so easy. We can always invest more money in our opportunity cost investment. That's simple. So if a project is right on the borderline, if the NPV is equal to 0, just do the simplest thing. Just invest in our opportunity cost investment. So let's do an example. Okay, so we've got distressed seller here offering you a treasury bond where the contract says in 1 year it's going to pay the holder of the bond $110, and distressed seller is asking you for $100 for this contract. So let's say our investment mission is per the above example. So we're a short-term investor looking for strong guaranteed investments here. So that would lead us to an opportunity cost investment of buying portfolio of CDs from as seen on bankrate.com. You can, I think you can even buy them from bankrate.com. I'm not sure, I'd have to double check that. Or our opportunity cost investment could be simply buy shares of the Mint ETF. And we've done our work as we did in the last chapter. We found that the corresponding opportunity cost of capital for either of those is 5%. And we want to know, should we buy the bond? Should we buy the bond? Well, let's see if we can figure this out using our steps for the NPV method. Okay, we want to apply the NPV equation here, and we're going to need to know our opportunity cost of capital and all our cash flows. Well, the opportunity cost of capital, we just figured that out, right? That, again, is the average of many CDs or the published interest rate of the Mint ETF. We do know the cash flows. The contract says we get 110 in a year. We could buy the bond for 100 right now. So those are all the cash flows. Now this one here is a little tricky, okay? Remember, all these cash flows need to be project risk adjusted. So the cash flow at t equals 0, that's adjusted because that's what we have to pay to buy this contract. So there's nothing we can do with that, the cash flow at t equals 0. That's adjusted. But the cash flow in the future needs to be risk adjusted. This is the contractual promised cash flow. But in this case, it's also the project risk adjusted cash flow. Why? Because if we have a stupid manager problem at the bank and the bank flames out, it doesn't matter. The FDIC is going to come in and pay us if the bank defaults. And remember, the FDIC is under the US Treasury, and there's very little risk to that. So in this case, the promised cash flow is equal to our risk-adjusted cash flow. So we don't have to worry about that. So we can jump right into the NPV. So applying the formula up here, I've got, what's my first cash flow? Minus 100. And if we wanted to be real pedantic about this, we could say 1 plus 5% raised to the 0, and as we know, anything raised to the 0 is equal to 1, so we don't have to worry about that too much. So then we'd say plus, oops, what happened there? Let me get this back in action. Okay, oh, and let's see. Nope, okay, got to write it again. Minus 100 plus 110 over 1 plus 5% raised to the what? This comes in 1 year, so we use our year time units and say 1, and that's looking pretty good here. And I can do a little bit of arithmetic on this one. That's minus 100 plus, if you work out this, I think what you will find here is 104.76. You should check me on that, of course. Okay, and so the NPV, if we work that out, is equal to 4.76. All right, so that's what we got here. Our NPV is equal to 4.76. So what does that mean here? Well, a good way to think about this is something like this, okay? Our NPV is equal to 104.76 minus 100. So if we write it in this way, we can say that the NPV is equal to, the present value of the flows that we buy. We're buying in present value in normalized terms, in t equals 0 terms, we're buying this 104.76 cash flow, and that is, we've got to say now, minus the price paid for these cash flows. Okay, so what do we have here? We have, just rearranging a little bit what I've got up here, I've got my NPV equals 104.76 minus 100, or in words, that's the present value of the flows that we purchased, only one in this case, minus the price that we had to pay for these cash flows, which was 100. So in this case, NPV is greater than 0, so we want to buy the bond, okay? And we're buying the bond because the NPV is greater than 0. Okay, good. So there are a couple of important and interesting interpretations of this NPV of $4.76. The first one is called the increased wealth concept. And the increased wealth concept says that positive NPV projects increase the investor's wealth by the amount of the NPV. So what do we mean specifically in this example? By making this investment, we've just made our firm richer by $4.76, the amount of the project's NPV. We have to remember that richer is going to be a relative term. It's going to be measured against making opportunity cost investments, not against doing nothing. So what we mean by making ourselves $4.70 richer is $4.70 richer than we would be if we just threw $100 into our opportunity cost investment. Okay, so again, when we say richer here, we mean that this is relative measure, not an absolute measure. And another way to think about it, again, is if we didn't make the investment in this project, what would we have done? We would have put our $100 into shares of Mint or our portfolio of CDs, which we know would have earned us an average of 5%. And both of these are projects with zero NPVs. Okay, so the logic of this is kind of important. We're assuming here, once we have an investment mission, whenever we get money to put into that mission, we're going to invest it. So we're going to look around for a positive NPV project, and if we find one, we'll invest the money in that. But if we don't, if, for example, you are this project manager and your friend gives you $100 to invest, if you look around and you can't find any good investments like the distressed seller investment, you're not just going to let her money sit there and not earn anything. You're going to put it into the opportunity cost of investment. You're going to put that $100 into shares of the Mint ETF, so at least the person who's given you the money is going to earn her 5% on that. Okay, so the second important thing we can say about this is called the equivalence concept. And the equivalence concept says that investing in this project is completely equivalent to receiving $4.76 today. How does this work? Well, let's consider that we have two choices today. So the first is we could invest $100 in the distressed seller project. And the second one is we could have someone just drop on our head, just out of the sky, just drop $4.76 on our head, and then we could invest the whole $104.76 at our opportunity cost of capital for a year, which is the life of our project. What the equivalence concept is saying, we have no preference between these options. Okay, so getting $4.76 dropped on our head and investing it in our opportunity cost investment is exactly the same as putting $100, not getting the $4.76 dropped on our head, and putting our $100 into the distressed seller project. And we have no preference between these two. So you can prove this to yourself by, on the one hand, find the future value of 104.76 invested at 5%, that's our opportunity cost of capital, for 1 year. You're going to find that that's equal to 110, and compare that to the future value of 100 invested in the distressed seller project. So here's how this would look mathematically. So if we get the 476 dropped on our head, we add that to the 100, invest that in the shares of the Mint ETF. We know we're going to get 5% on that, and you should work this out, but you should convince yourself that that comes out to 110. On the other hand, we don't get $4.76 dropped on our head. We invest 100 into the distressed seller project, and we also, as we've shown, wind up with 110, which is the contract amount for that project. Okay, this project is the distressed seller project, right? All right, so that's it for the NPV method. It's a very simple, very straightforward method. We just need to know for this method what all our cash flows are, when they occur, and we need to know our opportunity cost of capital. Then we just do the arithmetic and make it work. Okay, so our second method, excuse me, is our benefit cost ratio method. This is very similar to the NPV method, but now we're going to make a ratio out of some of the numbers. So the benefit cost ratio method is universally abbreviated as BCR, and we need to know what a BCR is. BCR stands for benefit cost ratio, as I said, and it's defined to be the present value of a project's cash inflows. So these are going to be positive, right? These are our positive flows divided by the present value of the cash outflows, and the outflows are negative algebraically. Okay, and of course we discount everything at the opportunity cost of capital. So now we're back to ratio analysis a little bit, and let's see if we can think about this. This is kind of a bang for our buck ratio. We've got in the denominator usually what we have to put into a project to enjoy what's in the numerator. So we want this ratio. This is a clear case where bigger is better. And in our ratio analysis chapter terms, there is going to be a knife edge here. So we'll think about that. All right, so bigger is better. And I think the knife edge is easy to see here. If the present value of the cash inflows is equal to the outflows, then we're sort of right on the border, right? So what we really want is we want the numerator to be bigger than the denominator, right? That's what we're really looking for. So this one would be what we would have called a knife edge in our ratio analysis work. Okay. Another thing you should know about the BCR ratio method is that some textbooks call it a profitability index. It means exactly the same thing. They'll just call it profitability index. Depends on the textbook. Some articles will call it a BCR, some articles will call it profitability index. It means exactly the same thing. All right, so there is a drawback of this method. The drawback is that the benefit cost ratio does not say how much wealthier the project makes us. So it's giving us less information than the NPV method. So the quants among you all would say something like this. It as a method is less robust than the NPV method. Okay, so this is a drawback. It's always good to know how much wealthier we're going to be by taking a certain course of action here. Okay. So now let's do our distressed seller example for the BCR method here. So we're still going to want to work with our NPV equation. because that's the equation that gives us the present value of all our future cash flows and the cash flow that we have for this project at t = 0. Okay, so let's plug in and get our ratio. So I want in the numerator the present value of all the positive cash flows for this project. So I think there's only one, and that's the one that's going to happen in a year's time. Okay, so that's going to be 110 divided by, I've got to present value it, okay, so I've got to divide it by 1 plus 5% raised to the 1. So that's my numerator. And in the denominator, I want the present value of all my negative cash flows. I only have one, and it happens at t = 0, so I don't have to worry about discounting it, because it's already sitting at t = 0. And we have something like that, okay? And if you work that out, you should check me on this. Should check me on all of these. Okay, I've got Excel right over here, but I'm counting on you, as you can see, more and more to check these numbers yourself. So I'm showing you the numbers and I'm counting on you computing them on your calculator to make sure I got it right. So since the BCR is greater than 1, since it's greater than 1, that means it's telling us to buy the bond. And you want to note that this is the same recommendation as we got in the NPV method. And that's always going to be true unless you've made a mistake. If you get a positive NPV for a project, that means you should go for it. Well, that's what the model tells us. The model says you should go for it. And if you do a BCR calculation on the same project, you should get the same recommendation. So if you get a positive NPV and a negative BCR, you've made a mistake somewhere. Okay, they're always going to work in the same direction. So let me just put that in here too. This is always the case. They're always going to recommend the same thing. They get there a different way, but they're always going to make the same conclusion. Okay, so our third and final method is our internal rate of return discounted cash flow method. So to get started with this, we need to know, what do we mean by internal rate of return? So here's a definition. You know what to do when you see a definition. You've got to memorize that sucker, right? So the internal rate of return is defined to be the discount rate of a project that makes the NPV equal to 0. So you just got to memorize that. Internal rate of return is the discount rate that makes the NPV of the project 0. Okay. And another way to think about it is it's the compound growth rate of an investor's money in this project. So you can think about it that way too. This is also very helpful. So I would recommend memorizing this too. So I'll put here that's also a helpful way to think about it. So now with that definition in mind, we can look at this mathematically. and say mathematically the internal rate of return is the discount rate that makes this equation true. And this is another thing you just have to memorize. It makes the NPV equal to 0. When we have the correct IRR in here, okay, we're going to get 0 for our NPV. So let's say memorize this also. This is important because this is always our first step in applying the internal rate of return method. We set the NPV equal to 0, and then we solve for what's the R or the IRR that makes that the truth, the whole truth, and nothing but the truth. So this is going to give us another way to evaluate our potential projects. So step 1 will be establish, as usual, our opportunity cost of capital and all the project cash flows. And then we'll solve for the IRR using these cash flows. And what's that going to mean? With the IRR method, if the IRR is greater than our cost of capital, the intuitive meaning of this, which is completely correct, is that our cash in this project is growing faster than our cash would grow at our opportunity cost of capital rate. So that's a good thing, right? We want our cash to be growing fast as possible. So that would mean what? We're going to go ahead with this project, right? Because if we go ahead with this project, our cash is going to grow faster than it would in an investment giving us our opportunity cost of capital. On the other hand, okay, if our IRR is less than our opportunity cost of capital, what's that telling us? That's telling us that our cash is growing slower than our cost of capital. So what should we do? We should definitely not go ahead with this project. We should put our money into our opportunity cost investment instead. So this gives us a really nice qualitative way to think about projects. That's the good news. The bad news is the IRR method has really big problems associated with it, so we can't always use it. Problem number 1 is just like BCR method, it doesn't tell us how much wealthier this project is going to make us. Like same problem we had with the BCR method. But the second one, which is more of a problem, is that we always have to solve this NPV equals 0 equation, and mathematically this means we have to find the roots of a polynomial or a real equation, which we looked at a little bit in the time value chapter. But the problem here is there might not be a real number solution that exists, and there's going to be more than one root. When we find the roots of a polynomial, there's more than one root, and we don't know which real root is correct. So neither NPV nor BCR have this problem, so they're definitely more robust methods than the IRR method. So let me show you an example illustrating the problem with computing the IRR. So let's say we've got this project. So at t equals 0, we'll make a loan of 100. At t equal 1, we'll get an interest payment. And at t equal 2, we'll get another interest payment. And we'll get our principal repaid. Okay, so with our NPV equation, setting it equal to 0 for the IRR, we're going to get something like this, minus 100 plus 10 over 1 plus IRR raised to the 1 plus 110 divided by 1 plus the IRR raised to the 2. That's fine. Now let's apply the magic of algebra. Let's multiply both sides by 1 plus IRR squared, and that's going to give us that 0 is equal to minus 100 times 1 plus IRR squared plus 10 times 1 plus IRR plus 110. All right, now this should start to look familiar to you from work you did all the way back in high school. Okay, so this guy here, I've got it again on this page. It's exactly the type of thing that we all were tortured with in high school, or maybe for some of you guys even in grammar school. An equation that looks like this. A parabolic equation, a quadratic equation set to 0. 0 equals ax squared plus bx plus c, except x is just equal to 1 plus IRR. Okay, once we make that little substitution, it's exactly in this form. So to solve this, we've got to find the roots of this second order polynomial, right, or parabolic equation. And how do we do that? We use what we were forced to remember in high school or grammar school, the quadratic equation, okay? And that looks like this. We can always do it by hand with this formula, or we could work in Excel, which clearly we can't do on exams. We could use goal-seek in Excel. And either way, we can find x equals 1 plus IRR, and then, of course, IRR is equal to x minus 1. And we find two roots, two possibilities for IRR. IRR equals minus 200%, that's probably not good, or IRR equals 10%. Okay, so this is getting difficult to do. And for longer duration projects, what if we had a cube term here? Or what if we had non-integer terms? What if this was 0.5? We don't have a quadratic equation for general things like that. So it's hard to find the answers, and we're going to find more than one IRR, and we're not going to know which one is correct. So let me give you one more example illustrating this. So here's a more complicated problem of longer duration. So we have 5 cash flows. We have this -1 at t equals 0, positive, negative, negative, and we want to find the IRR. So we just apply the NPV equals 0. So minus 3024 plus 17,172 over 1 plus IRR, etc., etc. You get the idea. Minus 12,000 over 1 plus IRR to the fourth. So now what do we have to find here? We have to find 4 roots of a fourth order polynomial. Okay, we could do this with goal-seek or a graphing calculator, and we could find 4 legitimate IRRs for this. Yikes. Okay, so 4. And you can plug these into your calculator and you will find they all make this equation true. They all make the right-hand side equal to 0, matching the left-hand side. So our problem with this is we don't know which one is correct. And also, if we work with goal-seek, if we start near 66.67, goal-seek is going to converge to this one. If we start near 33%, goal-seek is going to converge to this one. So goal-seek is just going to converge to one of these. We won't even know where the other three are or how they exist or anything like that. So that's a big, big problem here. But there's good news. We have math to the rescue, okay? Mathematicians have found in certain circumstances we can use the IRR. If we have projects like this where we have one negative cash flow and all the rest of the cash flows are positive, or if we have all negative cash flows and at the very end we get one positive cash flow, or the two other possibilities, which would be, this would be one negative cash flow here, one positive cash flow here, negative cash flow, negative cash flow, negative cash flow. Similarly here, if these three were positive and we had one negative, so we have a total of 4 possibilities that look like these. In these cases, mathematicians way smarter than me have found for us that the correct IRR for this project is associated with the smallest real positive root. So that would mean in a case where we have 4 of these, we'd want to choose the 25, something like that. However, important to note, IRR is not guaranteed to work on projects like this, where in general, we have a negative cash flow, positive cash flow, negative, positive. If we have positive and negative cash flows out in the future, it's not guaranteed to work. And if we look carefully at this one, we'll see that's exactly the case. Out in the future, positive, negative, positive, negative. It's only guaranteed to work where we have one negative, all the rest positive, or all negative, one positive, that type of thing. Or, of course, again, vice versa, right? Which would be this one, and then this is going to be okay too. Whoops. This is okay too. We have here one positive and all the rest are negative. That's going to be fine. And I could draw a similar cash flow diagram here where these 3 would be positive and this one would be negative. So there's 4 possibilities where this will work for us. The correct IRR is the smallest real positive root, but it does not work for these general random positive here, negative, positive, negative, who knows types of projects. So how does that help us? This means that the IRR, it's not good for some projects, but it's going to be very good for things like bond projects, right? Where we've seen exactly cash flow diagrams like this or like this if we're the borrower. So let's put in works for these. Okay, so for a bond project, the yield to maturity now is equal to the IRR. So the yield to maturity is the IRR when, I should say here, we use annual time units. Okay. So now we have another way to get the yield to maturity for a bond project. We just get the IRR and that's it. Okay, and remember from our chapter 8C, time value of money, YTM is also equal to the equivalent annual interest rate for bond projects. Also, IRR will work for things like loans, mortgage loans, other loans, So IRR is not hopeless. It does work for a very, very big class of problems, right? Bonds, loans, things like that. But we cannot use it for general cases like this. This would be a good real estate development cash flow diagram. You put in some money now, you get some money back when phase one is done, you put in more money to develop phase two, and then you get more money back when phase two is done. This type of thing happens in real estate development all the time. All right, so let's get a little recipe for using the IRR method. And the way this is going to work is if we want to evaluate a project with this method, as usual, first of all, we're going to define our mission. So for our short-term low-risk investor, that was we invest in guaranteed return one-year opportunities where guarantees are strong. And once we know our mission, we find our opportunity cost investment and get our opportunity cost of capital from that. For our short-term investor, opportunity cost investment was that diversified portfolio of one-year CDs or simply shares of the Mint ETF. And the opportunity cost of capital would be the average of the interest rates on the CDs or published rate of the weighted average interest rate of the Mint ETF. So then we want to, just like with the NPV method, find potential projects with similar riskiness. IOHO stands for in our humble opinion. Okay, so this is clearly subjective. Other people might disagree. So we find a potential project that we think has similar riskiness, determine its cash flows. Now that we know the cash flows, solve for the R that makes the NPV equal 0. That is the IRR. And now we apply our IRR rule, which is if the IRR we find is greater than the opportunity cost of capital, that means our cash is earning at a quicker rate than it would in our opportunity cost investment, so we want to go ahead. If the IRR is less than or equal to our opportunity cost of capital, we don't want to go ahead. Because if it's less, it means it's earning less than we get if we put money into our opportunity cost investment. And if it's exactly the same, the default thing, the easiest thing is to just put more money in the opportunity cost investment. So let's do our distressed seller example with the internal rate of return method and see how it looks. So our mission, again, is going to be invest in these very low risk one-year opportunities. And you know the story here. We find our opportunity cost investment and get our opportunity cost of capital from that. And then we're looking around and we find this distressed seller deal. Okay, same story. Distressed seller wants $100 for this bond now, and the bond contract says it's going to pay 110 in a year, and there's no intervening cash flows. So what do we do with the IRR method? We always start with just simply setting the NPV equal to 0 and then solve for that IRR. So what do I have? Minus 100 plus, excuse me, 1110. That's our promised cash flow in a year, which is also risk adjusted because it's a treasury bond, right? It was something that was very, very risk free, so we don't have to risk adjust it. And we divide that by 1 plus IRR, and that's raised to the 1 because it's 1 year out. And so that's going to lead us to 0.0 is equal to what here? 1110 over 1, let's see. Let me just take another couple steps to do this. Minus 100 times 1 plus IRR plus 1110. We'll just go slow here, one step at a time. And now we're going to have our 1 plus IRR is equal to 1110 over 100, and IRR is equal to 1110 over 100 minus 1, and that's equal to 0.1, and that's equal to 10%. Okay, so that's pretty good here. Let me just back this out, make this all look a little prettier. All right, so we find our IRR is equal to 10%, and that is greater than our opportunity cost of capital. 10% is, in most circles, greater than 5%. So when the IRR is greater than our opportunity cost of capital, means if we put our money into this deal, we're going to be earning more rapidly than we would be with our cost of capital. So that means that we want to buy this bond. Okay, and again, this is same recommendation as BCR and NPV. Again, the recommendation should always line up. The numbers will always be different, but the recommendations are going to be the same. So that's good. Okay, let's do another IRR example, just because these have all been a little too simple. So let's start out with our investment mission being similar to above, not identical, but close. So we're going to invest now in very low risk 1 or 2 year opportunities. We go out to bankrate.com, look at 1 and 2 year CDs, and the Mint ETF we can still look at. It's got some stuff that matures in later than a year, so we're going to say it's close enough even for 2 year investments. So we still find that our opportunity cost of capital is 5%. So now we want to know, should we buy a US dollar denominated German government bond that costs 100, and the contract says it'll return back 112 in 2 years with nothing in between, so that makes it a zero coupon bond. All right, so let's see if we should buy this one. So we're going to do the same thing here. We've got the NPV equation, and for the IRR method, we always want to set the NPV to 0. Okay, so that's going to be minus 100 plus 112 over 1 plus IRR now raised to the 2. Now we have something a little less trivial here in this case, okay? And if we do the algebra on that, let's see if we can do the algebra on that. We have 0 is equal to minus 100 times 1 plus IRR raised to the 2 plus 112, okay? And so then we get 1 plus IRR squared is equal to 1112 over 100, and that's looking pretty good. And I think from that we can get directly that the IRR is equal to the square root of 112 over 100 minus 1. And if you work that out, you should confirm that you get 5.8%. Okay, so let me put it there, confirm this. Okay, so confirm that at home. Okay, so the IRR in this case, 5.8%, and that is greater than, greater than our opportunity cost of capital, which is still 5%. So that means our cash would be growing faster in this investment than in shares of the mint, than in our opportunity cost investment. So we want to go for it. Okay. All right. Hopefully that has made some sense. So I'm going to pause here, and then we're going to pick up in a second with a real world example. And we'll solve this example, this analysis, should we buy the bond example, using IRR, BCR, and NPV. But let's take a little break right here.